Alright, in this section we're going to talk about lattice energy. When we are talking about polar and covalent bonds, it's really easy to talk about having an H2 because I have two H's bonded together. I can separate that, I can work with that. When I'm talking about an ionic bond, on the other hand, and I have Na and Cl, it's not that simple because it isn't just a discrete unit of Na and Cl. I also will have a Cl here that's attracted to the Na, a Cl here, a Cl here, one in front of it, and one behind it. So I will have 6 Cl's for every Na, and I will have 6 Nas for every Cl, which is why these ionic compounds form crystals. And it's not, you don't talk about them, you do simplify it down to the simplest form of it, the NaCl part, but when you're trying to look at it, you can't look at just this bond, you have to look at all of these bonds involved in there. And so we look instead at what's called the lattice energy of the bonds there. And this is going to remind you a lot of Hess's law. It is related to Hess's law in that both of them are state functions. And remember, a state function is its independent path. It doesn't matter how I get there. The energy is going to be the same if I go from here to here, or if I go from here to 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 there, right? I traveled the same distance, I just did a lot more of it, and they cancel each other out. So, if I want to see what the lattice energy is for an ionic compound like LiF, I'm going to take, and I will need an Li and an F to have made that. So I'm going to look at these independently and build back up to this. So I'm going to start with Li solid, and I'm going to have to change that to a gas. So I'm going to look at the energy required to change that to a gas. I'm going to look at F2, which is a gas, but I only want one F. And I'm going to have to look at the energy involved in breaking that bond. I'm going to also have to look at going from Li to Li plus and losing that electron. So what is its ionization energy? And then going from F to F minus, and what is its electron affinity. If I know all of these things, I can add them all up, because that will get me back up to this if I put all those things together, and I can say what the lattice energy of my molecule is. The lattice energy is going to depend, like we saw before with our equation, the E equals K Q1 Q2 over R, on how big of a charge I have, on my nucleus this time, and the distance between the nuclei. So they have a really good example and diagram of this on page 345. And here's one that I just found online. So if we want to know the lattice energy for sodium chloride, here are my different things that I'm going to have to look at. So here's one pathway that I can go through. Here's the other pathway that I can go through. This side is the ones that I'm going to know, and to be able to look at. Well, this side we can figure out later from independent study. So here, if you look, is where I'm going from a solid to a gas, the energy involved in going from a solid to a gas. Here is the ionization energy going from sodium to sodium 1 plus. Here is the breaking energy, taking the Cl2 and breaking it into the separate pieces. And here is the energy involved in getting rid of that electron. If I follow this through, then I can find what my energy between these two should be, which would be my lattice energy.